at this. We're on test 12, finally. All right. So we're looking at chapter 10, and then 22:1 and 22:2. Okay, all of chapter 10, remember, was covered here? And then 21:1 and 21:2. So the first two sections of chapter 10 and the parts of 22 are all theoretical stuff. So there's one thing in 22:2, the solenoid, that we talked about direct and indirect variation. But there's no math involved, it's more how you understand the relationships that exist. There are no calculations that would happen. The calculations, they're going to come from 10.3 and 10.4.
What's the deadline for that extra credit? The extra
If you do the problem sets, it'll be before Monday. I mean, before your test. If you do it after the test, it doesn't serve a purpose, so I'm not going to give you extra credit for that. If you do it before the test, sure, and it's not extra credit, it's just counting as a homework completed, which in essence becomes extra credit for some people. But if you have a homework average sheet, technically of 100, turning in another homework that's right, doesn't actually increase your grade. You know what I mean? It keeps your homework average 100. So, but I don't think anyone has a homework average 100 actually, because it involves problem set grades. So 10.1 and 10.2, what did we learn? There's a lot of theory there, right? First thing we started with in 10.1, we had to really start with to understand what we were doing. We defined something to start in 10.1. What was that term? Heat was in 10.1 and 10.2, but before that even. Before heat, we defined something else. We talked about thermal equilibrium. These are good. I should just write them all down because these are good things. But we started with temperature. These were key terms that we looked at here, right? Heat, thermal equilibrium, and temperature. So let's start with temperature because we need to know what temperature is to understand heat. Without temperature, heat doesn't make sense. So temperature to start, if you recall, was how quickly the molecules are moving. The average kinetic energy. It's really the study of the motion of the molecules of the particles. So if something is hotter than another thing, it just means that its particles are oscillating or vibrating at a higher rate. Now, when something cools down enough, it slows down that oscillation. It can't cease to oscillate, that's absolute zero. So if you recall, absolute zero is the absence of any motion of the molecules. I gave you guys the example. Why can't you get to absolute zero? I gave you like a theoretical example that works. Well done, Will. So think about like with a refrigerator. You want to cool down a drink, I gave the example, or an ice bath. You would put it in something colder than it to make it colder. How do you get something to absolute zero? You can't have a container colder than absolute zero. So you don't have a container that can cool it down. So as a result, you can never get anything down to absolute zero actually. And it's also the idea theoretically on a molecular level that everything has some motion. Anything with mass has some sort of energy to it. So as a result, it has that internal energy defining its temperature, which again is really the kinetic energy of those particles. Now, with temperature comes heat. What is heat? What is heat? And don't give me the exact definition. Give me your, you could read it obviously, it's in your notes to see if a lot of you swiping. But how would you interpret heat? How would you interpret heat? What do you think? That's good. So heat loss or heat gain is that, yeah. We talk about heat loss and heat gain with objects that are in contact via conduction, convection, radiation, but more specifically, like just the term heat in general.
Is that just like energy is transferred from one time to an object?
Yeah, we're looking at the transfer of energy in general, and we're talking about specifically due to a temperature imbalance. Okay, those two things are really important there. That it's a transfer of energy in general, you can have loss or gain, and it's due to a temperature imbalance. Thermal equilibrium means? Thermal equilibrium? Kind of the opposite of heat. What's thermal equilibrium if you think of it as the opposite of heat? Exactly. When the hot and cold balance each other out, or they eventually come to a state of equilibrium, means they have the same temperature. Thermal equilibrium means two bodies have the same temperature. Is your body in thermal equilibrium with the room right now? No, definitely not. What's the room temperature right now, you think? Probably 70 or below with the air conditioners on, right? Your body, we said the other day we were measuring, remember, it was like 80, 90 on the surface. Inside, 98.3 or whatever it is. 6? I'm thinking of, there was a radio station when I was a kid in Long Island, 98.3. So thermal equilibrium. Now, when we look at problems with calorimetry, calorimetry involves the loss of heat from one object causing a gain in heat in the other object, or energy, I should say. Loss in energy in one object causing a gain in energy in another. So as a result, when this happens, those objects eventually lose enough heat where the other one gains enough heat where they come to a state of thermal equilibrium. So calorimetry involves heat, it involves temperatures, it involves thermal equilibrium. All these terms are used for calorimetry. And for calorimetry, this is where one of our key math problems comes from. There's two math problems we're going to look at: calorimetry and then temperature/phase change. The heating curve problem and the calorimetry problem. The calorimetry problem is really only important because that's what allowed scientists for a long time to determine the C value, the specific heat capacity of any substance, by comparing it to water. Water was the baseline. Everything's based on water. Do you realize that? Think about it. The Celsius temperature scale was created based on water. The value of C for water, 4.186 times 10 to the third, was like our baseline, our first C value that was then used to compare against others. What's the density of water? What do you remember? What's the density of water? It was 1 gram per cubic centimeter, or 1,000, but it's on the order of 10. Do you see how everything for water works out to be like zeros and tens and hundreds and certain values? It's because a lot of the scientific principles we learned were fundamentally based on water. So it's important in this unit to understand that for calorimetry. So calorimetry, we can say the following: the energy lost by one thing is the energy gained by the other. Q1 equals negative Q2. The loss by one is the gain of the other. The negative portion is indicating loss of energy here. Okay, loss of energy. So if I know what the substances are, and I know what the mass is, and I know what temperature change is going to occur, I can find the C value of one of the substances, or I can find the mass of one of them. What is the Q in this problem equal to? Is it MC delta T, or is it ML? Do I use MC? It's one or the other. Do I use MC delta T for both parts here, or ML for both parts? Which one is it? Why? There's A in temperature. M1 C1 delta T1 equals negative M2 C2 delta T2. This, again, folks, listen carefully, not given on your formula sheet. MC delta T is, but Q1 equals negative Q2, that's theoretical. That's the idea. Write it down if you don't understand it yet, or haven't memorized it, or really gotten a grasp on it. The energy gained, Q1, by one substance is equal to the energy lost by the other, Q2. This is simply, what is this really? Conservation of energy. MEI equals MEF, really. But in this case, we know in the beginning, this one gains energy, and this one loses energy. So we know that Q is MC delta T. That's on the formula sheet. So you can substitute with those formulas right there, and that can come from the formula sheet. But you need to know to use that. Don't use ML. ML involves a phase change. We are not dropping iron in water and the water's boiling off. We're assuming there's no phase change occurring. It's just an elevation of temperature in the water causing the hot metal to cool down in temperature. Okay, when one gains, the other one loses. Delta means change, so please remember that this formula then becomes the following. Okay, final minus initial. Final minus initial. If you're not given the final minus initial, but you're told that the water's temperature changes by 40 degrees Celsius, how do you approach the problem? If the water temperature went up by 40 degrees Celsius, not told initial and final, you're just told that the water went up by 40. George? So you could pick like 20 and 60 as your numbers, but instead of that, George, isn't 40 just the change in temperature? So would I need this last line here in white? I would use the yellow one here. I have change in temperature, right? Take a look at this, folks. If you're told that the temperature change is 30 degrees Celsius, you can just plug 30 in right here. Okay? Final minus initial would mean this would be ready. Say this would be 50 minus 20. And that would give you overall change in 30. Yes? It depends on what you're given. If you're given the initial temperature of the metal is 15, the water change is 30. That means you're told Ti2, which you have to put here, this whole thing will have to be 30. You have to solve for the final temperature of the metal. Okay? So you have to adapt to the problem. If you're given the temperature change, you don't have to replace it with Tf minus Ti. You can just replace delta T with that. If you're not given a temperature change, you have to replace it with Tf and Ti. Please, we have an example. It's example 1 in the notes for 10.3 and 10.4. I highly recommend you study that. Okay, it's a perfect example for this. There's also homework examples you did, and if you look at the problem set, those are good practice problems. There's 1 or 2, I think, with calorimetry involved. Okay? Now, the second part of math for 10.3, 10.4 involves temperature and phase changes. So we know that a substance that's a solid, its temperature is going to elevate, then it's going to melt, temperature elevates as a liquid, then it boils, then temperature elevates again. So in the other class, I'll probably get through a little bit more, or just watch the other part of this video. So this is our standard heating curve here. We know that when we see a flat line involves a phase change. Because what's the y-axis really? What is the y-axis? You got it? Temperature. The y-axis is temperature. What's the x-axis? For a heating curve, what's the x-axis really? The amount of energy. Very good, Ernest. As you increase the temperature, don't you also increase in energy? To change a phase, what do you need more of? Energy. So take a look, ready? In the beginning, by gaining energy, follow the cursor. Okay, in the beginning, by gaining energy, you gain temperature. Take a look, please, up here. This is what slope is defined as, right? As you gain energy, you gain temperature. Well, then suddenly, you have no slope, which means you're gaining energy, but you're not gaining temperature. That means that you're changing phase. Then you gain energy and gain temperature. Then you just gain energy, which means you change phase. So now you're a gas, and then you change temperature as you gain energy. So you got liquid and solid. I'm sorry. You got solid to start, liquid and solid, then liquid, then gas and liquid, and then gas. No. Water from negative 20 degrees Celsius to 30 degrees Celsius. Tell me what's happening. Water going from negative 20 all the way to 30. What's physically happening here? George, go for it.
Well, it's going to, it stops at 0. At 0, it changes
Into?
states.
From what to what?
From a,
At negative 20, what is H2O?
negative is in gas.
At negative, it's low temperature.
Okay, so it's going to a liquid.
From a
Solid.
solid, not a gas, right? So when it's really cold, it's a solid. You have ice. This is a freezer temperature, right? So 0 is the freezing point. So this is a freezer temperature. Oh, thanks, Mr. J. The other one worked, though, too. The other one worked fine. Yeah, the other balance we have is in caliber. No, yeah, we don't even need it at this point. We'll use it for sure. It'll be faster. Thank you very much. The other class will use it. So yeah, we're going from a solid into a liquid. Mr. Joseph, is this familiar?
Yeah, of course. It's good for them
Right.
also.
Yeah, they're doing well with it. We're going from.
If you don't remember this, then
Did you go from-
I just jump over the window.
Did you go from solid all the way to gas and
Yes.
calculate all 5 stages?
Yeah, they've done it.
So look at this. So I'm expecting perfect scores on the test for this now. Thank you for your words. You can't lie. And we've talked about this before. We're just staging this, obviously, you know, right? So from negative 20 to 30, let's go through this. So as you said, from negative 20
0.
All the way to 0, we have a temperature change. At 0, we have a phase change. And then from 0 to 30, a temperature change. So tell me, please, we've done this enough now, you should know. What formula do I use for each stage, for each part? There are 3 parts to this problem right now. What formula for each part do I use? Give me the first part.
The first one is Q equals MC delta T.
Very good. For second part, what do I use? Somebody else for the second part. For the second part. Nick, go for it.
Is that a Q? Is that another Q equals M L?
Very good, Nick. Well done. And the third part. The third part. Use the context, right? Obviously. Come on, yeah. Yeah, I know you know. Again. Yeah, MC delta T again. Ladies, focus. Stop talking so much. MC delta T. It all agrees for the third part. Now, if the object isn't changing mass, I don't need to have M1, M2, M3. Just call them all M. Does that part make it clear? But the C value and the L value is different for all 3 of these. C of ice is different than C of water, which is different than the L, which is the latent heat of fusion. This is LF. Why is it LF and not LV? What does LF stand for? This is just memorization at this point. You need to know what LF stands for. Yeah, from a solid to a liquid or liquid to it incurs freezing or melting is when you use LF. When it involves evaporation, V for vapor, evaporation. That would be LV, or condensation, which is the opposite of evaporation. When you've got gas and it condenses on the side of something and you see liquid droplets, that's condensation. It's going from gas to liquid. So in this problem, we'd have to know how much mass is involved. Or maybe, like in the homework, I give you the total Q and you have to figure out the mass. Or maybe I give you the total Q and you know the mass and you know the temperature changes, and I ask you, figure out the L value involved. And you have to just solve for L. But here's what we know, ready? Here's what we know. After this, we can say Q total is equal to the sum of those 3. So I've got this. Okay, this is what I've got. Now I only use 3 for Q3. There's no Q2 anywhere. There's no C2 anywhere or delta T2 anywhere. Don't let that bother you. I just jumped to 3 because it was Q3. But together we know that the total amount of heat necessary to cause this ice to go from ice at -20 to water at +30 involves the sum of these 3 parts. Elevate temperature, change phase, elevate temperature. So if you're given the total amount of energy, where does that go? Where would total amount of energy go if you were given that in the problem? What would you substitute in for total amount of energy? Q total, please, right? We all see this. Q means energy, total means total. So the total energy would go here. M is mass. If you have to solve for mass, you got to plug in all the other numbers and then think about mass and use these as like terms. These are your coefficients in essence. We did that with the homework example. Look back at that, please. And I went over that in class for the homework. If you're given the masses, hypothetically, and you're given Q total, maybe you have to figure out what the L value is. So you'd have to be given everything else and determine L. Maybe you're not told the final temperature. Maybe you're not told that it gets to 30 degrees Celsius and you're told it turns into water, but we don't know what temperature it ends at. Then you have to figure out the final temperature for water over here, TF. You make that TF minus TI again. So it depends on the context of the problem what you need to solve for. Ernest.
I was going to ask, so like if you don't know the mass, would you just take the mass out, so it would be like Q total equals M times C delta T?
And all of this would add together and it would become the coefficient of the mass, which is the same thing as combining like terms. But you can factor it out, but don't divide by n. You can factor out for n here, get all the other numbers, you'll get one number for all those, and that becomes the coefficient for n. Okay? Very good question. So again, you could solve for any of these things at this point. Whatever it is you could solve for. What am I forgetting from chapter 10? Let's go into our modes of heat transfer. Our modes, by the way, you notice we have double, so only 20 like 4-minute periods. I'm going to continue the review as if it's a 45-minute period. What about our modes of heat transfer? We had 3 modes. Give me one of them and tell me something about that mode. 3 modes of heat transfer. Really important. Okay, this is the key way we go about life. It really is. These 3 modes of heat transfer. It's so incredible when you think about it. Conduction is one of them. Can you tell me something about conduction?
Basically, a transfer of energy.
Okay, but give me more than that. What is involved in conduction? There must be physical contact. You gotta have contact. No, necessarily, sorry. You gotta have contact, physical contact. That's the key for conduction, okay? It does not occur without contact. Without contact, it's either convection or radiation. It's one of those two. And technically, convection involves contact, but involves what kind of contact for convection? Contact of a fluid, liquid or gas, a fluid in general. Now, can somebody describe conduction and describe convection a little bit more? Like, what do you see when 2 things are touching in this conduction? What can you tell me about temperatures and such? And then with convection, what can you tell me about the fluid and how it flows? There's more to it than just these terms, right? Give me a little bit more.
I know convection is the liquid transfers and from the energy it transforms into a gas state.
It can do that. Okay, go ahead. Keep going.
And then it moves down again and then it goes back to liquid.
So you're describing the thermodynamic cycle of like an air conditioner, which involves convection. Now, which part of it is really convection? They're both technically convection, but the convection that we know for coolant, right? For coolant is when the liquid fluid flows over the surface and it decreases its temperature. So remember what we talked about with food? When your food is hot, what do? Because it's fluid, the gas or the air from your mouth is colder than the actual food. So you go, fluid is flowing over the food, cooling it down. The air conditioner creates fluid flow, that air drops, it's cold air. The warm air rises, gets sucked out of the room. Cold air comes back in. Warm air rises, gets sucked out of the room. How does the cold air come in? That's what Will was describing. When the cold air comes in, it involves a thermodynamic process that transfers heat away from the air it's coming in. So ready? This is crazy to think about this. Are you ready? The air comes in the room. There's like Sarah and George. The air comes in the room. It gets cooled by the coolant. That coolant is what evaporates and then gets recondensed. So the coolant itself is very cold. It's called freon. Freon is the word for it. I use the term R134A. It's a coolant. The coolant cools down the air. It blows cool air into the room and it pulls out warm air. Okay, that's how this process works. So convection, again, involving fluid flow. Tell me more about conduction. You want to tell me about conduction?
Well, you said the hand, put your hand on the table. Your hand, conduction is warmer than the table itself. So that's why you have noise when you pick up your hand because it transfers heat.
Very good. That's where the moisture comes from on your hand. That's where the table, why it looks the way it looks. You're transferring the heat, again, by conduction. What can you tell me about the general temperature gradient around my hand? The general temperature gradient, that was a word I used, around my hand. Right around my hand, the temperature of the table is going to be what?
It goes out from hot to cold.
Very good, John. It goes out with contours from hot to cold. So this is hot right here, colder. And then after that, the rest of the table is pretty much just cold, right? If I attached, or if I took, imagine like a really hot coal ember from a fireplace and dropped it right here. Besides burning, maybe melting this material, probably not melting because this is made from lamps, but burning the table, it would create a heat gradient or a temperature gradient throughout the rest of the desk. Probably better than your hand would. Okay, so this would be like a high temperature, lower temperature, even lower temperature, until you get to like cool temperatures. Okay? But that's what it would look like with the temperature gradient for conduction. So again, convection we talked about also. How about radiation? We didn't really go into a lot with radiation, but we did say something. Radiation involves what? What does radiation involve? Waves, good. It involves energy carried by waves. And what's the interesting part about this? It makes it different from conduction and convection also. It can travel through a vacuum. Without a vacuum, without a medium, convection cannot occur. Fluid has to occur in a medium. If it's not going to occur, there's not going to be convection in it. So this travels long distances through a vacuum. Obviously, conduction doesn't work through a vacuum because it involves contact, right? In a vacuum, there's nothing in it, so there's obviously no contact. Yes?
Is it waves carrying waves or waves carrying energy?
Jeez. It's obviously waves carrying energy. Thank you. So it involves waves carrying energy through a vacuum, or can be through a vacuum. I think that's it for chapter 10. Trying to think of anything else. Did I miss anything? Anything in the notes you want to point out, or something you looked at with your questioning? Chapter 10. Maybe look at like 10.1 or 10.2. See if there's anything I missed there. Oh, I missed thermal expansion. Thermal expansion, what is that? We talked about a lot of applications of thermal expansion, but what is it physically? The general trend is, George?
As like temperature increases, so does the volume.
Very good, George. Okay, this is what we're looking at. As T increases, V increases. Thermal expansion. Next year, I think we're going to do the math of this also. Because then I realized the math we did was only specific heat capacity. I should have done the math of this. And had I known, you studied this in chemistry last year, but you didn't do the math involved. If we look at the math, there's these coefficients like alpha and stuff, which are called thermal expansion coefficients. And we can see how much the volume of the substance will expand based on its alpha value. It's like C. How much the temperature increases based on the heat added. Alpha is how much the volume increases based on the heat added. So I'll probably include that, but just know that you can do math with this. That's the general trend. What are some applications we talked about, or what are some ways you've seen this before? Because I'm going to give questions on the test. Maybe there'll be multiple choice, maybe there'll be short answer, but it will involve some sort of application for sure. So give me some examples of applications of thermal expansion. Thermostat is the easiest one, very good. The mercury expands, or the iodine, or whatever it is, expands. Or with some thermostats that involve a dial, the metal expands differently, causing the dial to move. Yeah?
It's a
Hot air balloon.
The volume increases as
It's really the buoyant force that increases. The volume barely increases. The balloon expands because it's capturing the hot air. But I wouldn't use that example. We're talking more about materials expanding. I guess air and gas is a material, so it naturally expands, which makes it less dense than the air around it, which causes the buoyant force. So with a lot of explanation, that would work. Okay? But more materials applications. What are materials with expansion that are? What are materials? I hate when that happens. What is the answer? What are materials that expand based on their thermal coefficient, or the thermal expansion coefficient? I talked about a lot of these in class. Come on, other stuff.
I don't know what material you said it was, because like the subway platform would expand.
Those extend and contract, yeah, they do. Which probably involves a little bit of thermal expansion. In the summer, the metal changes, but something else is not like that.
You're talking about how like doors are stuck or it's like too hot.
Yeah, in the summer, doors will swell up because of heat and humidity, and they'll get stuck. Literally, they get stuck shut. Wood in general expands when it's hit higher. The bridges, remember the bridges? When you go over the bridges, you have those interlocking parts. Because of expansion and contraction in the summer and winter, the bridge needs to be able to deviate a little bit in shape and size. So these little teeth allow for movement, and yet cars can still go over it. If those teeth weren't there, you would get huge potholes. In the wintertime, don't you guys see potholes in the ground all the time? It's because of thermal contraction in the winter. The molecules contract in the asphalt, so as a result, if they contract too much and cars keep going over them, it causes weak points where the actual stuff will break. It will actually like start to split. You know when you bake cookies? When cookies are done, how do you know they're done? How do you know cookies are done? You look at the color, but there's another way to do it. When you look at the top of a cookie, what do you start to see? Those little cracks start to form? It's like that. Imagine concrete where those little cracks start to form. Why do they start to form? Because the actual material contracts. Not the same reason as cookies, where they bake But I want you to visualize that. That's what's happening in the concrete themselves. Little cracks form in the wintertime, your car rolls over it, causing it to break. As it breaks more and more, the pothole forms. And then your car goes over it, you feel like, right, in the wintertime, potholes form a lot. And then they get mended in the springtime. No. In the normal road that you travel on, it would crack. In a bridge, this won't happen. You don't want it to happen in a bridge. But on a regular road, it can easily be caved, right? So a regular road, it can allow for expansion and contraction. But on a bridge, you don't want that. So when that cement can expand and contract, as a result, you have these interlocking plates every so often to allow for expansion and contraction without that happening. It allows the bridge to physically move. Okay. And it helps with vibrations too. The vibrations that bridges occur, the swaying, gets absorbed more by this location, this little junction. Yeah.
Don't some bridges have it because they like hold up?
Absolutely. That's more of a locking mechanism, for sure. For sure. Those are drawbridges, yeah. But I mean, if you go over the GWs, that drawbridge, it has those every like 100 feet, you're going to see the locking mechanisms. Okay? Yeah, and also for vibrations, for sure. Okay, it's multi-purpose. So let's move on now to magnetism. Let's move on to magnetism. We started with the idea of magnetism in the beginning, and we looked at the idea of magnets having poles. Somebody give me a little rundown on the basics of magnetism. Give me the information they know. Just spitball at this point. Go ahead. Okay, opposites attract. So if I have north and south, and another magnet here, this magnet is north and south, this would be attraction. Very good. Opposites attract. Lauren.
If you were to like cut magnet in half, she's like a smaller version of the magnet, that would be like separate.
Very good. So if I cut this in half, it creates another south pole and a north pole right there, pretty much creating two smaller magnets of the same thing. Ernest.
The Earth's magnetism poles is actually, the north pole is actually south, magnetic south. The south pole is actually magnetic.
Very good. So we know that the poles are reversed, really. Okay, MS and MN is magnetic south and magnetic north. Why is magnetic south deemed the North Pole? What's the idea there?
As a result, if you have a compass, you would put north towards
Attracts toward
on the south.
magnetic south. North attracts the south, so the north needle compass, the north end of the needle on the compass would be attracted to the magnetic south, which directs you to the North Pole. Hence the names. We know that magnetic fields come out of the North Pole and back into the South Pole. What else? We talked about permanent magnets. We talked about induction to create a permanent magnet. We gave an example in class where, if you recall, we were talking about wires and solenoids with an electromagnet here. Induction involves having a magnetic field near or in the proximity of a ferromagnetic material. Ferro standing for iron. Material with iron in it, usually iron, other things are magnetic also. But ferromagnetic materials in general, if you have one of them and it is near a magnetic field, it will induce a magnetic charge on that material. So you might go from a material that is not magnetic. Stop, guys. Stop screwing around. You might go from a material that's not magnetic, and then suddenly the poles get aligned. And I talked about magnetic domain theory, and we had all these little pieces of the magnet, and the little particles were not aligned. So let's zoom in on this. We had this, where some of them, the magnetism was angled in one direction, and the others it was angled in a different direction. So these are not aligned at all. This is what an unmagnetized material looks like. The polarity of the actual molecules are not lined up. Now, you bring it in the presence of a magnetic field, and suddenly what happens to all these arrows? What happens? They all point in the same direction, pointing toward the North Pole of that. So under the presence of a magnetic field, suddenly all the arrows point up, or all the arrows point in one direction. The direction the arrows all point are just like a compass needle. The compass needle points north. Well, what we call North Pole, because it's magnetically switched, obviously. All right. We talked about the right-hand rule. The right-hand rule involved a wire. If the current was traveling in the wire, and the current was traveling up in the wire, which, by the way, have you seen that show? Great show. The Wire. Has anyone seen The Wire? It's the best of all time on HBO acclaim. The best. You know that? That and The Sopranos are the top 2 watch shows of all time. More than Game of Thrones, more than like even new shows. The Wire is an awesome show. If you have time to kill in the summer, you have HBO Go and you want to like watch a show, I'm telling you, it's an amazing show. It's about, you know what it's about? The Wire? It's about wiretaps. Back in like the 90s when police came out, when police and wiretaps came out, how they actually used to use technology to advance, apprehending criminals. It's a great show. Watch it for sure. Anyway, a current carrying wire produces a magnetic field. Here's what we do. We imagine that this eye pencil is the wire. Put your thumb in the direction of the current. Your fingers show the direction of the magnetic field. So from here, if I'm looking from below, I would say that the fingers go this way, right? From below, my fingers go this way, which is clockwise. So how would I draw this here? I would say that it goes around like this, from below. Take your thumb and look at the way your fingers would curl. They would curl this way, right? So you see the way I drew this? If they curled this way, then I would draw it like that. These would curl this way. So thumb up, fingers like this. What if I said to you, the current in a wire was into the page? There's out of the page and into the page. This is something that I didn't go over because it's really in 22.3, but it's useful. You should really understand it anyway. So I might make an application of this. If the current is coming out of the page, take your thumb and do this, please. Put it out of the page. Look at your fingers. Which way are they curling right now? What's this called, though? Counterclockwise. If the current's into the page, which way are my fingers curling? So when that happens, the magnetic field, in this case, would be clockwise, the magnetic field, and in this way, the magnetic field would be counterclockwise. Okay, review the last part we talked about with a wire that's coiled over itself. And it's the last part on solar as we just went over that in class. Okay? Make sure you study for Monday, get the problem set in for extra credit, and watch it. Okay, it's an extra homework.